Hello everybody, how are you all? I hope all of you are doing really great. I welcome you to yet another live session on the subject of kinematics of machinery. Previously in the different sessions we have discussed many concepts on machines, machinery, mechanisms, links, etc., their motions and their velocity, accelerations, then how they are moving in a definite paths and all that. So I hope all these live sessions are helping you a lot in clearing different doubts that you had and different mind glitches that you had regarding the subject. I hope in the further sessions also you will get some or the other benefit. So let us see what this session has for you. So today's class we will be discussing, today's live session is going to give you insights about cams and followers. Now you must be wondering what is a cam and how is that following, how is the follower following the motion. So let us see what exactly is a cam. This unit is a fourth unit in your syllabus for kinematics of machinery. Let us come back to the definition of the cam. Cam is nothing but, it is a rotating element. It is sometimes sliding as well, but it is generally a rotating element which is mounted on a camshaft and on which on this diagram you must be seeing, it is very easy to understand it diagrammatically. This particular rotating element is nothing but a cam. So I say a cam is a rotating element which is specially used in transforming the rotatory motion into a linear motion. So when I say that this particular element is a rotating element over here, which is called as a cam, and now coming to this particular element which is said to be a follower, this follower is nothing but is a translating or a oscillating element that follows the profile of the cam. Okay, so let us see how that actually works. So this particular rotating element is rotating, actually mounted on this shaft which is called as a camshaft, and here this particular element is let's say reciprocating and following this particular profile of the cam. So you can see that this is a roller kind of element. So we'll learn about the classification of followers. Let us first learn that this is a roller kind of follower. So this is how a cam and follower motion is progressing. So next slide we will be discussing how the followers are classified. Let us see. Classification of followers are basically divided into three different ways. So first one says according to the shape in contact with the cam. Which is the shape? How is the shape given to the follower which is in contact with the cam? Based on that the followers are divided. The second basis of division is how is the motion of the follower. The third one is according to the location of the axis, which is let us say it is coinciding with the center of the cam or it is at the offset. We will see the different classification in the next slide. But this is the basic division of the classification of the followers. So let us learn for each one individually. When I talk about the shape of the contact, shape in contact with the cam, they are basically divided into three different parts. First one is the knife edge follower, the second one is the roller follower, and third one is the flat faced follower. So in the example you can see this is a knife edge follower. In the name itself it says it has a knife edge. That means it has a very pointed edge. So here you can see there is a knife kind of edge over here which is following this cam profile. So whenever you are rotating this cam, the follower is going to let's say follow this particular path. We will learn about the nomenclature a little later and we will know how that is named. So second one called roller follower. See, you have a circular roller over here. You have just seen, see this is the same roller kind of follower. So this is nothing but the roller follower. Here also the follower is reciprocating in nature. This is the profile of the cam on which the roller is following. The third one is a flat face. In the name itself it is very clear that it is a flat faced follower. So the face of the follower is a flat surface kind and which is following the profile of the cam once again. Here also the motion of all the three kind of followers are shown to be reciprocating. You see this is double-headed arrow which is saying that the follower is going to move up and down and reciprocating in this way. So let us see what is the next classification. According to the motion of the follower. See, this is the motion of the follower. I told you that is reciprocating. Reciprocating it, let us say, it is going up and down. So first kind of the follower is the reciprocating type of follower. The second one is the oscillating type of follower, where the follower is arranged horizontally. You can see the difference over here. It is arranged vertically, and here it is arranged horizontally. Whenever it is following the profile of the cam, the follower is able to only oscillate up and down. That's it. There's no reciprocating, no linear motion. Actually, there is only a little of curve that is oscillating over here and here. Let us see the next kind. According to the location of the axis of the follower. So location of the axis of the follower, suppose this is the axis of the knife edge follower. If it is coinciding with the center of the axis of the cam, suppose it is coinciding with it, it is collinear, so I'll say that it is a inline kind of follower. If it is an inline kind of follower, what do you mean by inline follower? Inline follower is wherever the axis of the follower and the axis of the cam are lying on the same line. So if you say like that, then you can see in this diagram, in this figure, that you have the axis of the follower and the axis of the cam on the same line. So this is inline kind of follower. So next one is the offset kind of follower. You must be knowing what is called offset. Offset is nothing but it is having certain distance from the actual axis. So where you can see here also in the example, this offset kind of follower is having a certain distance. This is the offset that is provided. This is the center axis of the cam and this is the axis of the knife edge follower. They are not coinciding, they are not lying on the same line, but they are actually a little away from each other. So when they are away from each other and following the same parallel distance all through, I can say that they are at a certain offset. So if they are at certain offset, they fall under the category of offset kind of follower. So here, you know, this is a cam profile. I'm talking about so many technical terms. Where did they emerge from? We will learn about all those technical terms about cam and the nomenclature and the naming, etc. in the topic called nomenclature of the cam profile. So nomenclature of the cam profile is what actually? When you talk about a cam and a follower, say an engineer and let's say a layman or the person who doesn't know anything about this technical terms, how will he understand about the namings and everything? So there should be a certain distance. So an engineer is always learning about the technical terms. How is it exactly called? As a draftsman, whenever he is going to design, he will understand only those terms. So in a way to understand that, they are giving certain technical names for the parts, certain parts, right? So let us say, this is how the cam profile is. You can see this particular, the continuous line that you can see over here is the cam profile. So this particular line is a cam profile. Sorry. This particular line, this particular dark line is called as the cam profile. On this cam profile, you can see the roller follower is able to follow the path. This is the roller follower that is given over here. So this is the roller follower. So you can see all through the roller follower is following this particular profile. Hence this particular curve or this particular profile is called as the cam profile there. So see, you have a pitch point, you have a trace point. What is a tracing point? In the name itself, it is tracing the path of the cam profile. So see, this particular center point, whenever it is following that, let us say the cam profile, all the time the diameter is going, the distance between these two is going to be same everywhere. So this particular point is called as a tracing point. Alright. Next comes the prime circle. So this particular circle, the dotted circle, this particular circle is called as the prime circle over here. We will learn about why we are learning about this is, see, in this chapter the main aim and the main type of questions that they ask in your end semester exams, be it any university or be it any evaluation method that they ask, they are always asking about the construction of the cam profile. So only to understand what kind of technical terms that they will be giving in the problem, and based on that how are the construction methods applied. You must be knowing what these particular terms are. What is a trace point? What is the prime circle? What is a base circle? All this, what is the least radius, etc. These all terms are very, very important in a point of exam point of view. So let's learn what is a pressure angle. So see this one, the normal that is drawn over here and the angle over here from the center of this particular roller follower. You see this is the phi angle, this which is a pressure angle over here. So follower motion is again given as a reciprocating motion over here. We are always majorly considering that the follower is only following a reciprocating motion here. Next, the pitch point is this point. Again here, base circle. This is the circle that is a tangential circle to the cam profile. You can see that is the base circle. And cam rotation is having a clockwise rotation here. The cam rotation is given as like this. So it is a clockwise rotation. Clockwise rotation. I told you what about a cam profile. This is the pitch curve which is passing through the center of the profile, and it is always, let's say, equidistant or parallel to the cam profile. We should be drawing this pitch curve whenever they are asking for the construction of a cam profile and they are giving that the follower is of roller type. We must be aware of that. We should draw this pitch curve all the time whenever they are asking about the roller follower. Okay, so let us learn about each definitions. So first of all, the cam profile is the surface in contact with the follower. We discussed just before in this diagram, wherever the follower is touching, follower is following all the way over here, we say that the surface that is traced over there is called as a cam profile. Next comes the trace point. It is a reference point of the follower for the purpose of tracing the cam profile. So how a cam is going to move, what is the profile it is generating? Whenever you are having a trace point, locus of all those points generated together is going to give you a cam profile. So what is it? Base circle. It is this basic, let's say, smallest circle drawn from the cam center, because cam is not, let's say, circular shape. It is again of different shapes. Let's say drop shape, pear shape, and then wedge shape. There are different types of cams also classified. So base circle is nothing but from the center of the cam. If you draw a basic smallest circle, that particular circle will be called as the base circle. Next, the prime circle. It is the smallest circle drawn from the cam center. Next comes the pitch point. It is the point on the pitch curve having the maximum pressure angle. Wherever your pressure angle is maximum and the point on the pitch curve with the pressure angle be maximum, that particular point is called as a pitch point there. Next comes cam angle. It is the angle of rotation of the cam for a definite displacement of the follower. Next comes the pressure angle. It is the angle between the direction of the motion of the follower. That's why they have given, see, the direction of the motion of the follower is like this, and the normal, if you draw at that point, that see, the normal to the pitch curve if I draw, and to the follower motion of the follower, if I take the angle between them, that is called as the pressure angle. Next is the pitch circle, the circle having the center at the center of the cam and radius equal to the distance between the center of the cam and the pitch point. Yes, so that is nothing but the pitch circle. Till here you may be getting a, let's say, theory answer, or let's say just the nomenclature, but these 2 points, let's say life or stroke, or let's say period of the dwell, this is also called as lift also. It is also called as lift or stroke, and the period of the dwell. These 2 points are very, 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 very important in this whole nomenclature. So let us see what is the stroke. It is nothing but the maximum travel of the follower from the lowest position to the topmost position. So total stroke, when I say, when you consider, let's say, other subjects also, you have, let's say, the strokes in a piston cylinder arrangements also. So stroke is nothing but from there also you can understand then when the piston is traveling from the topmost corner to the topmost end to the bottommost end, that is nothing but taken as one stroke. So here also the follower is traveling from the lower position to the topmost position, and again from topmost position to the bottommost position. So let's say the one whole travel from bottom to top, that particular length is taken as to be the stroke. One stroke is the maximum travel of the follower whenever it is going from the lower position to the higher position. Next is a period of dwell. Now this is a new term, period of dwell, dwelling period. Let's say the follower is dwelling for certain angular displacement. So dwelling is what basically? Dwelling is nothing but whenever you have certain resting period. So literal meaning of the dwelling is nothing but you are on a rest or hibernation, that kind of period. So yeah, of course the cam and the follower arrangement also gives certain kind of dwelling period. See, for the first slide when I showed you here, see, it is at this, let's say it's not moving for certain time, right? It is on a resting position. Once it is going to the topmost position, then resting for certain time, then again it is lifting. Then again coming down, then again resting for certain time. So that resting period is nothing but called as a dwelling period. So period of dwell is that the resting period, or let's say is a period of during which the follower remains stationary. Stationary means it is not moving, neither going up nor going down. It is a stationary during some finite rotation or half rotation or a 1/4 rotation. Let us say how much of that rotation is, that rotation time, the follower is not moving, it is just stationary. So that particular period or time period is called as the dwelling period of that particular follower. So now we have learnt about the motion of the follower, the cam, the technical terms, the nomenclature of the cam profile. We have learnt about all of them. So let us see how the follower is, let's say which kind of motion is the follower able to give. Let's say, what is the behavior of the motion of the follower? So motion of the follower is basically given into 4, 5 different, this 1, 2, 3, 4, 5 different types. So let us say first one follows a uniform motion or a uniform velocity kind of behavior. So whenever you take uniform motion, that means it is neither rising nor dropping drastically. It is following a linear path, right? It is proportionate in x and y direction. So that is how the meaning of uniform motion or uniform velocity is justified. So let us say first one is a uniform motion or uniform velocity type. Next is SHM, where you have simple harmonic motion. We know how the simple harmonic motion is given in sine curve and etc. So let us see, that is, we will see individually in the next slides. First let us discuss what is the follower may have motions. So third one is uniform acceleration and retardation. The acceleration and retardation are nothing but acceleration is a positive quantity and retardation is nothing but the negative quantity of the same acceleration. So we will also learn about uniform acceleration and retardation. Next one is cycloidal kind of motion, and the last one is any type of desired motion that we give for the cam profile, the follower is able to follow. So motion of the follower is given whenever the cam profile is given of any desired shape. So these two type we will not be discussing in this session because these three are prescribed and most important. These two are also there, but in this session we will not be discussing these two. So let us talk about the first one, uniform motion or uniform velocity, how the behavior is given. See, here the displacement, first of all we have three things. The displacement, velocity and acceleration. So displacement is here, the cam is rotating, yes. So if the cam is rotating, the displacement is never going to be linear, right? So cam is rotating, the cam is transmitting certain rotatory motion into reciprocating motion. So first of all we will have some, let's say cam rotation into angular displacement. So angular displacement here, let us say 0 degrees, 90 degrees, 180 degrees, 270 and 360. So we have taken the one whole rotation where we have divided into 1, 2, 3, 4 and 5 divisions, where you have, it is starting from the 0 degrees, it is reaching to 90 degrees, then we have it divided into straight line 180 degrees, then 270, then 360. So how the motion is distributed in this 0 degrees to 360 in displacement point of view, let us see. See, whenever it is lifted up, right, the follower, this is the cam, suppose, if the cam is rotating and it is on the topmost, let's say here it is starting. So if I am moving it up, the follower is able to move up. So it is moving upwards. So uniform motion, so it is going upwards. Then it is able to stop, it is let's say resting for certain period, stationary. The follower does not move at all, it is stationary. So period of dwell is there. Again it is going to come down, right? The follower is able to come down. See, reciprocating motion, right? So one it is going up, then staying, let's say, stationary for some time, then it is coming down. Then again it is staying resting for some time, then again it is coming down. So that the behavior is rising up, then dwelling, then falling down, then again dwelling. Okay, so equal divisions of let's say the rotation is taken from 0 degrees to 90 degrees to 180 to 270 to 360. Okay, accordingly, if I draw the velocity diagram, okay, so if it is a uniform motion, uniform velocity increase will be there. So let us say from here, of course the velocity is increased, so I'll draw one rectangle over here. Dwelling period, so rest, there is no velocity, zero velocity. Here it is a fall, so negative velocity, let us say it is lesser velocity, very less velocity. Then again here dwell, so again zero velocity. That is how is the velocity diagram drawn here. Next comes the acceleration diagram. So at the acceleration, you can see at the 0 degrees, infinite acceleration is given, right? How is that justified? When you are increasing the velocity, how do you increase the velocity for a vehicle? If you are accelerating it, right? So if the velocity is reaching its highest position over here, then that means that you have accelerated to the infinite position. So here at 0 degrees itself, you can see infinite increase in the acceleration. The same thing continues till here, and since it is a drop over here, you will have an infinite reduction in the acceleration. Same thing over here also, infinite reduction in the acceleration. Same thing follows over here. If you see a curve over here, it is going to uprise till 0 degrees. So again here also, you have increased the speed or velocity till acceleration over here in infinity terms. Then comes dwelling or the rest period till the 360 degrees. Now, I ask you that is it possible that immediately whenever you are starting a vehicle, it accelerates and you reach the highest speed? Of course not, right? It is obvious that you have to gradually increase the speed and then you will reach to the, let's say, a particular speed or a higher or peak speed, right? Immediately if you start the vehicle and you raise it, you will not reach the actual, let's say, peak velocity at once. So this is nothing but a hypothetical or a theoretical approach of having the velocity and acceleration diagram. So for this, what they did was they have modified the same velocity and acceleration and displacement diagrams, and they have given they have given the modified diagram to be like this. A small curve is mentioned over here. This curve mentions there is a gradual change. There is a gradual change here. So this is possible, isn't it? If this is a gradual increase in the speed, of course, gradual increase in the displacement, because instantly if you start the vehicle, you will not reach the destination. You have to gradually move along. So gradual increase in the displacement and then gradual fall in the displacement over here. Accordingly, the velocity and the acceleration diagrams are given. So when you have the mathematical terms, mathematical expressions out of it, let us see. First define, let's say S is equal to the stroke of the follower. Stroke or what is the stroke? First of all, we have seen the stroke to be the maximum lift that the follower is taking from the lowermost position to the highermost position. So this is nothing but the stroke of the follower S. Then X is nothing but the lift of the follower when the angle is turned by theta after time t. So theta naught is nothing but the outward or the outstroke angle. Then theta is nothing but angle turned by the cam in time t. And omega, as we also already know in the previous session, we have discussed about this. This is an old term, right? This is omega, angular velocity of the cam, because cam is a rotating element and it is not going to have any linear velocity, it is going to have an angular velocity. So let us have the expression. So the displacement is, displacement diagram I have taken. So from 0 degrees it is going to rise over here. So if it is a rise, then this is going to be the stroke, okay, and this is going to be the theta O, outstroke, right? Outstroke angle, because this is in this x direction we have taken theta. This is the stroke. Now if I draw any certain, let's say after time t, this is nothing but, let us say, some x distance. The lift of the follower is some x over here. And let us say I have taken after time t, there is some displacement of theta over here. So let us have some other color. Theta color, theta. Okay, so if I want to write a mathematical expression, see here also they form what? A similar triangle. Can you see? This particular triangle, if you see, this is nothing but the stroke, this is x. This is theta naught, this is theta. If I want to write the, let's say, the equation, mathematical equation for this, how will that come? X is equal to s by theta naught into theta. Why? How this has come? I will write x by theta is equal to s by theta naught. Why? Because similar triangles. So x by theta is equal to s by theta naught. And if I take this side, x is equal to s by theta naught into theta. Okay? So this is how we have come, since x by theta is equal to s by theta naught. So here we have got x. And we already know that angular displacement is nothing but angular velocity into time. Displacement is equal to speed into time, right? So angular speed into time. So if I substitute in place, you have x is equal to s by theta naught into omega into t. But we want velocity. If I want to find out the velocity, this is nothing but the displacement. So if I want to find out the velocity, how will I go further? If I have x term or the displacement, if I differentiate it with respect to time, we get the velocity. So here also same thing is given, dx by dt. If I differentiate that, we have got this equation, v naught is equal to d by dt of this particular x term. And finally, v naught is equal to s by theta naught into omega. Why this t has gone? Because t is nothing but again differentiated with respect to t. So differentiation of t with respect to t is going to give you 1. 1 multiplied by this particular term gives you again same term, s by theta naught into omega. Now s is the stroke, constant value, outstroke, constant value, omega is also angular velocity of the cam. So this particular total term is going to be certain constant term, right? Some constant value. Let us first know. Next, we have learnt about velocity. Now next we will go for the acceleration. So we already know that if I know displacement, if I differentiate with respect to time, this particular term is going to give me velocity, right? Again, if I give velocity, if I have, let's say, dv by dt, this particular term is going to give me acceleration. So same thing we will do over here also. For acceleration, we will differentiate this velocity term and we'll see how did we get it. See, acceleration of outstroke will get d by dt of this particular term, s by theta naught into omega. And in the previous slide, we have said that this particular term is going to be some constant value. So if constant value is differentiated, of course we will get 0. So that's what we have got, 0 here. Next is here see modified, I told you how the modified displacement and velocity already explained. So let us see how they look like. It looks something like this. See, they have given the curves over here. Can you see the curves? Instead, in the previous slides they had a sharp edge, but here they have given curves over here, and over here. So this means this is practical actually. This kind of displacement diagram actually happens. So this is a modified displacement, velocity and acceleration diagrams. Based on this displacement diagram, the velocity diagrams are given like this. See, slide change. This now shows the gradual increase of velocity, gradual decrease of velocity. Again, gradual further decrease of the velocity and gradual increase of the velocity, and then dwelling period. Similarly, here also acceleration is not going to the infinite term. It is going to a certain finite term. Acceleration is finite over here. So let us now next we discuss about simple harmonic motion type of motion of the follower. Simple harmonic motion, we already know that it follows a sine curve. So let us see how they are, let's say how the displacement diagram is drawn. The method of drawing the displacement diagram for SHM kind of motion of the follower is nothing but, first of all, they will give you the, let's say the stroke of the follower will be given. So let us say stroke is given, certain stroke will be given, and they will ask you to find, let's say first calculate the displacement diagram and then further go for the cam profile construction. So basically let us say if some stroke is given some 4 or 40 mm. For example, this is just an example that I am giving. So if I say that they are giving some 40 mm diagram, 40 mm for the stroke. So with this 40 mm, what will I do? I'll draw one straight line of 40 mm distance. Then take the midpoint of this and draw a semicircle. Then divide this circle into 6 equal parts. Okay. For this, they will also give the cam rotation, let's say outstroke rotation, dwelling rotation, return stroke rotation, and again dwelling rotation. So let us say some angle is given. So I will extend this line such that the length of the line is going to be equal to theta O plus theta D plus theta R plus theta D. Total length of this particular rectangle is going to be this. And the width is going to be the length of the stroke. Now in this we will classify further. Suppose theta naught is given some, let us say 60 degrees. So you take 60 mm line. So here theta is given in degrees. Degree is a rotation. So how to convert? Now we have to project here in linear way. How to project that? So here we will take a scale. How we will mention the scale? Let us say 1 degree is equal to 1 mm. So here 60 degrees will become 60 mm. 60 mm if I convert into centimeters, it is 6 centimeters. So say 6 centimeters here is the outstroke. Theta naught. Next comes dwelling. So similarly, let us say some 120 degrees of dwelling. So 120 degrees of dwelling, again 120 mm. So it is 12 centimeters there. Then theta R is equal to some 90. This is also some 90. Suppose they are giving like this. So here accordingly we will divide it 90. So this particular thing is again return stroke. Okay, this particular rectangles over here are left to be dwelling. Okay, so here since now next step is we have to check how many parts is the circle divided. Half circle is divided into 6 equal parts. So let us divide this theta naught and theta R into 6 equal parts again. Let us take another color over here. So I will divide it into 6 equal parts. 1, 2, 3, 4. So first part, second part, third part, fourth part, fifth part and sixth part. Okay, so this particular rectangle is divided into 6 equal parts now. Same thing here also. I'm dividing this rectangle into 6 equal parts again. Okay? And from each line over here, let us draw the projection. Okay? So let us say here 0. First one is first division is 1, 2, 3, 4, 5, 6. Here we will start with 6 dash, 5 dash, 4 dash, 3 dash, 2 dash, 1 dash and 0 dash. Okay. So we have 6 divisions here and 6 divisions here. Here you have the projection from, let us say, P, Q, R, S, T and U. So projection line from P horizontally and projection line from 1 horizontally meet at this particular point, this particular point. Similarly for second line and Q, they meet at this particular point. Similarly for the third point, it is here, fourth point it is here, and fifth point it is here, and sixth point it is here. Again for 0 degrees also the point was here. So if you trace this particular curve like this, let us say this is how do I, let's say ABCD, A, here A, B, C, D, E and F. F and G. Okay. If I start from here, A, B, C, D, E, F and G. F and G. So here you have this curve over for the outstroke angle. Same thing we will decide here, or we will point out here also. Let us say it will follow on the sixth part, U line over here, and then fifth line over here, 4, 3, 2, 1 and 0. So if you trace this curve like this, it is going to generate a curve, let's say curve path over like this. Okay, so this is nothing but the method of drawing a displacement diagram whenever the condition of the motion of the follower is given to be simple harmonic motion. So let us see how the velocity and the acceleration diagrams are given. So this is how we have drawn the displacement diagram. This is how the displacement diagram is drawn. We have seen, see, 1, 2, 3, 4, 5, 6 divisions here, and 6, 4, 5, 6, 5, 4, 3, 2, 1 and 0 divisions there. This is the outstroke angular displacement, that is the return stroke angular displacement. The circle, half circle over here is going to be divided into, let's say 6 equal parts here as well. So this particular left out part is nothing but dwelling over here, and remaining part is also dwelling over there. Accordingly, when you draw the velocity diagram, it is going to follow a sine curve from here, let's say from here till the sixth line over here, outstroke. Then return stroke, it is going to be a reducing of, let's say negative sine curve, so over here. And similarly, when you differentiate velocity, you are getting acceleration. So when you differentiate sine curve, you get a cos curve. So you have the cos curve for the acceleration. This is the acceleration diagram. You can see from the, let's say this is the first positive curve for the velocity diagram. You have the cosine curve for this, cosine curve for this. So here also we have the technical, let's say the terms used are stroke of the follower, this displacement, the angle turned by the point moving, then theta naught is nothing but the outstroke angle, theta is nothing but the angle turned by the cam, and omega, as we know, it is the angular velocity of the cam. So when you have the previous method is same followed over here, derivation is not that important. Let us first just know the formula for the outstroke and the return stroke maximum values, that is given as pi into s into omega by 2 theta naught. Wherever it is outstroke angle, theta naught. Whenever it is a return stroke, it is a theta r. Similarly, when you have maximum acceleration for the outstroke and return stroke, you have the same thing. You have to differentiate the same over here. You will get pi square into s into omega square by 2 into theta naught square. And similar way, it is for the return stroke, just the theta naught changes into theta r over here. Why we are discussing all this? Because in the construction of the cam profile, finally they are going to ask about determine the maximum velocity for return stroke and outward stroke, and maximum acceleration for outstroke and return stroke. So that's how this kind of formulas are important for that point of view. This formula is only valid when you have, let's say, SHM kind of motion of the follower. It will be mentioned in the question. We will discuss one of them in today's class. So next comes uniform acceleration and retardation. So uniform acceleration and retardation, also we have different method for drawing the displacement diagram. Here we do not draw the semicircle. You cannot see a semicircle over here. But here also the stroke will be given. Stroke length will be given. So this is nothing but the stroke length. With the stroke length and the summation of theta O plus theta D plus theta R plus theta D, you will draw the length, and width will be the stroke. You will draw a rectangular part and then subdivide like this: theta naught, dwelling, theta R, and then finally dwelling. Okay. So for each part you will divide them into again 6 equal parts. You can see 0, 1, 2, 3, 4, 5 and 6. There also 6 dash, 5 dash, 4 dash, 3 dash, 2 dash, 1 dash and 0. So when you see that, you have a midpoint or a mid-center line as on 3. So since you have divided this particular angular displacement into 6 equal parts, you divide the center line also into 6 equal parts, and from this 0, try to join all of them over here. I will draw and show you if required. So I told you that there will be stroke. So stroke will be given. With stroke you draw the length, and let us say draw a little big so that it is visible properly, and the length is going to be the summation of, this is the summation of theta naught plus theta D plus theta R plus theta D. Okay, that is the length. So here we individually going to divide. Let us say this is theta naught. Then again theta dwelling. What is this? Theta is nothing but the angular displacement that the cam is rotating about. Okay. So theta is given as the angular displacement here. So this is nothing but the return stroke, and again remaining is dwelling. So each part we are going to divide like this. Okay. I told you that each part you again divide into 6 equal parts. So 1, 2, 3, 4 and 5. Draw the vertical lines. This is nothing but the method of drawing the displacement diagram whenever the condition of the motion of the follower is given to be uniform acceleration and retardation. This does not follow any SHM motion of the follower. It is following about uniform acceleration and retardation. The same equal parts you will divide for the return stroke also. 6 equal parts. One, 2, 3, 4, 5 and 6. 6 equal parts. So Here, let us write down to be 0, 1, 2, 3, 4, 5 and 6. Here we will write it, let us say 6 dash, 5 dash, 4 dash, 3 dash, 2 dash, 1 dash and 0. Okay. So this third line being the center, or let's say center line, okay, because we have 3 divisions here and 3 divisions that side. So third line is making a sense of being a center line over here. So this particular line also has to be divided into 6 equal parts, because this total division is 6 parts. So 1, 2, 3, 4 and 5. Let us name it like A, B, C, D, E and F. So from here, let us say I'll join each point till here. And from here like this. Okay. So when you see these two lines are intersecting, you find these points over here. First line and the AO line is intersected over here, these points. Second line and the B point, this one. Third and C here. 4 and D over here. 5 and E over here. 6 and F over here. Okay, so these are the points that are to be traced. So if I, let's say, trace it again, this is the curve. The green color one is the curve over here, which is traced for the uniform acceleration condition of the follower and during the outstroke of the follower. The same thing will be repeated over here also on the third line. Let us say on the third line we will again have the division, this line 1, 2, 3, 4 and 5. So here also you have, let us say, E, D, C, B and A. So here we will join it like this. And like this. Okay, it follows the same line anyway. Here also we will have the point of intersection. You can see the point of intersection being, let us say, on the first line here, on the second line over here, third line here, fourth line is here, fifth line is here and sixth line is here. So again, while tracing the curve, if you want to trace the curve, just join those points. And you have the motion of the follower whenever it is uniform acceleration condition during the return stroke. So this is what is the method of drawing the displacement diagram whenever you have the condition of the follower to be uniform acceleration and retardation. The same thing was discussed in the previous slide like this. So this is the one, and accordingly if you differentiate this this quantity, you will get the velocity, and this is how the velocity diagram looks like. And subsequently if you further let's say differentiate this velocity, you have the acceleration diagram to be like this. So when you have the diagrams already drawn, we already know what is the stroke of the follower and beta and theta naught, theta r. Here theta naught is nothing but the angle of outstroke, theta r. These two terms are repeatedly used because these are the main functioning of the follower. Because during the dwell it is only being stationary. So theta naught and theta r are nothing but outstroke angle, angular displacement, and return stroke, angular displacement, and omega is nothing but the angular velocity of the cam. So for uniform acceleration and retardation condition, the maximum velocity during the outstroke and return stroke are given like this: 2 into s into omega by theta naught, and 2 into s into omega by theta r. And maximum acceleration is given as 4 into s into omega square by theta naught and 4 into s into omega square by theta r. Now comes the most important part of this total session, construction of the cam profile. How to construct the cam profile? So for this cam profile, there are few inputs required. What are those inputs? Let us say First of all, you need to know what is the least radius of the cam. Least radius will be given. Least radius, then you also should be knowing what is theta naught, theta d, then theta r and theta d. Okay. For this, for construction the cam profile, these quantities are important. Also, you should know which condition is it following, whether it is SHM or uniform acceleration or uniform velocity. It may follow any of the condition. So first of all, you should take care of what condition, what inputs are given. Also, you should know whether the cam is rotating, cam rotation is clockwise or counterclockwise. You should also know whether the cam is rotating clockwise or anti-clockwise also, because I'll show you how it matters. So these all inputs if I give, or if these conditions are already given, then we will be, also stroke is also required. The stroke will decide how the displacement diagram is drawn. Okay. So let us once try how to draw one. Let us say stroke is given. Okay. And theta naught, theta d, theta r and theta d is given. Okay. And condition given to be some SHM. Why this is important? Based on this, the displacement diagram will be drawn. And we have seen how different kinds of methods are there for drawing the displacement diagram. If it is SHM, we have to draw a semicircle, and if it is uniform acceleration, there is no need to draw. Right? So let us say this is the condition given. So what we are doing is basically, let us say first we are drawing the displacement diagram accordingly. And this length is going to be the total length of the summation of theta O, theta D, theta R and theta D, right? And then when individually we are dividing it into, let's say 4 individual parts, this being theta naught, this is theta D, theta R and this is again theta D. Okay. So semicircle means, SHM means we are dividing the semicircle into 6 equal parts and we are drawing the projections. Like this. And since this is divided into 6 equal parts, we are dividing the theta naught also into 6 equal parts. Further, the return stroke was also divided into 6 equal parts, sorry. And we have seen how to name them. Let us say 0, 1, 2, 3, 4, 5 and 6. This is 6 dash, 5 dash, 4 dash, 3 dash, 2 dash, 1 dash and 0. While tracing the points, we know it is the intersection points over here, like this, and here also it follows the same. So if you trace the path, it is going to follow like this. Okay. So let us name it be, let's say A here, B, C, D, E and F. Similarly here also F dash, E dash, D dash, C dash, B dash and A dash. Okay. So I told you that your least radius will be given. Least radius will be given. The construction of cam profile begins here. First of all, this is nothing but just to draw the displacement diagram. From here, we will be able to construct the cam profile. So for that, first of all, least radius will be given. So least radius, with the least radius, some diameter will be given. So you draw the circle with the help of the least radius. Now, on this circle, you divide this circle into the angular displacement that is given. Let us say theta naught, theta d, theta r and theta d. So let us say this is the center line. Okay, and this is given as, let us say, clockwise rotation. So the cam is rotating this way. So if the cam is rotating this way, the follower is going to trace a path in the, let's say, left hand side. Yes, so it is going to generate a path on a left hand side. The profile is going to be this side. Suppose the cam was rotating in anti-clockwise, the difference it would make was the profile would be generated in right hand side only. So that is the only difference that is made. Okay, so let us say let us coming back to here. Let us erase this because this will cause problem. So here we have a center. On this center, let us first, theta O is given. Let us say it is some angle theta O. Let us draw that theta O. On the basis of this, again, let us say some theta R is given. Theta D. Next is theta R. And remaining is theta D. Okay? Theta D. Now here theta naught is divided into 6 equal parts. Here also we will divide this into 6 equal parts. 6 equal parts. Here also theta R is divided into 6 equal parts. So here also in angular basis also 6 equal parts. Like this. Now comes the crucial part. Here you see in the displacement diagram you have a distance from this first point to A point. Measure that 1A distance and let us say this is the first line, second line, third, fourth, fifth and sixth line. Here also this is 6, 5, 4, 3, 2, 1 and 0. This is dashes. So here from the circumference of this least radius, measure that 1A distance and make a curve like this. Similarly 2B, from circumference over here 2B. 3 and C, so 3 and C you curve. Then 4, 5 and 6. So you get a curve like this. Draw the curve with a free hand. Leave it like that. Coming to the return stroke part, what happens here? 6 dash. So from F, from the sixth line to F. From the sixth line to F, here, no, let's just say here. Same distance over here. From the bottom till here. Same distance. Then from here to E. From this distance F. Then from here to E. E, let us say it will reduce a little from here to D, then here to C, third line, second line, first line and 0 here. So here also you will get another curve like this. So this is nothing but the deciding factor of the cam profile. Okay, very nice. So here you have a curve where you know that the cam follower is going to be stationary here. So how the tracing of the point will be parallel to the least radius. Like this. Parallel to this particular circle, the least radius of the circle. And here it will follow the same profile. So let us trace that differently so that it is visible properly. So see, this is going to be the profile of the cam. This is going to be the profile of the cam. Is the method clear? Is it okay? See here, I will give the summary at the end of the session. So this is how you draw the, let's say the cam profile construction is given. Okay? So based on that, if I have a problem like this, let us say it is saying that draw the profile of the cam operating a knife edge follower. Here see here in the previous session I told you the cam profile is there, cam profile construction is there. Here we will solve this problem totally and we will know how this knife edge follower can be included. So here they are saying that the profile of the cam is operating a knife edge follower where the axis of the follower is passing through the axis of the camshaft. This is very important. Axis of the follower is passing through the axis of the camshaft. There is a difference. I will tell you how the difference what difference it makes. From the following data, see the question will be given like this: the follower to move outward through 40 mm during the 60 degrees of cam rotation. So it is moving outward, okay, through a 40 mm distance. 40 mm is going to be the stroke, okay, and 60 degree of cam rotation is the outward angle. So I'll say that this is theta naught is equal to 60 degrees, okay. Similarly, follower to dwell for next 45 degrees. So here we will say that theta d is equal to 45 degrees. Next, follower is to return to its initial position. It is going back to returning to the initial position. So return stroke theta r is equal to 90 degrees. Similarly, follower to dwell for the rest of the cam rotation. Rest of the cam rotation, how can that be obtained? Total rotation is 360. This is 360. These three angles are given. So 360 minus 60 plus 45 plus 90. So 360 minus the summation of all the three will give you the remaining part of the cam rotation. So that is the thing given. The next, the displacement of the follower is to take place with SHM. The condition is given. See, the SHM condition is given. I told you that this condition is very, very important. SHM during both the outward and return strokes, it is given. The least radius is given. Least radius of the cam is given. If the cam rotates at 300 rpm, n value is given. Determine the maximum velocity and acceleration during the outstroke and return stroke. So the problem framing will be somehow like this. There are different ways that they can ask. I told you the axis of the follower is passing through the axis of the camshaft. This is an inline kind of follower. So whenever you are drawing the follower, it should pass through the axis of the least radius. That is, you should make sure. Suppose if it is not passing through the axis of the follower, it will be something, the offset distance will be given. You should draw the axis, you should draw the follower, let's say whichever follower they will give, knife edge or roller. After drawing axis of the follower, axis of the cam, you take a certain distance parallel to the axis of the cam and you draw the follower right there. I will discuss that a little later. So let us say, let us solve this problem. What all are given? Your stroke length is given 40 mm. Then theta naught is given 60 degrees. And theta d is given 45 degrees. Then theta r is given some again 90 degrees. Then theta d is remaining. So remaining you can actually leave it. You do not have to actually calculate and write it over here. It does not matter. So again we have to note down that it is given the SHM condition. Okay. So SHM condition is given. Then you also have least radius. Least radius is given to be some 50 mm. Then that's it. So based on this, of course, this is also talking that it is the axis of follower passes through axis of the cam. So here same way like we have drawn just before, we will draw the SHM kind of displacement diagram just like this. Since I have discussed this just now, right now I am not going in detail. So here theta d, theta o, then theta d, theta r, and remaining angle we don't know, theta d. Okay. So again same thing, you have to divide this semicircle into 6 equal parts. Okay. So this condition we have discussed. Suppose in the same problem they are giving uniform velocity or uniform, let's say, acceleration. So how this is going to change? We are not going to draw this one. We are not going to draw. We are going to draw the displacement diagram like this. With the stroke length, we will draw a rectangle. And first division is going to give us the outstroke angle, theta naught, then dwell, then return stroke, and remaining is theta d. Then uniform acceleration condition, how do we draw this displacement diagram? We are dividing this particular part into 6 equal parts. And the middle point we are dividing again into 6 equal parts. Then we are joining these two lines like this. And then we are generating the curve like this. Just giving the, let's say, over here. Like this, the curve is generated. If it is uniform acceleration condition, we are drawing the displacement diagram like this. And accordingly, we will take the displacement distances here and then we'll generate that cam profile. So here comes, they are asking, determine the maximum velocity and maximum acceleration during the outstroke and return stroke. So for this formulas are important. Uniform velocity, because it is SHM condition, so we will use this pi and s and omega. So here they are giving what? They are given 300. N is given as 300. N is equal to 300 RPM is given. So you know that omega is equal to 2 pi n by 60. So you convert that into omega and then substitute the value over there. You will get the value for V0 and VR. Similarly for F0, F0 is nothing but the acceleration over here. Maximum acceleration during outstroke and maximum acceleration during return stroke. So this is how you will solve the problems like this. And now there is one more kind that they will give, that is for the knife edge follower. I told you that is important. So whenever you are generating a, let's say, cam profile, suppose this is a circle, a least circle that you have drawn and you have taken, let us say, the first let's say the theta naught outstroke angle, then dwell, then return angle, then dwell, theta O, then theta D, theta R, and this is remaining angle theta D. So suppose this is going to be the axis of your cam rotation. So initially you are going to draw the knife edge follower like this over here. Actually, when they are saying that the axis of the follower is passing through the axis of the cam rotation, this is going to be the condition. Suppose they give the axis of the cam follower does not pass through the axis of the cam and it is at the certain distance or offset is mentioned, what you will do is for this axis, you will take a certain distance parallel. Let us say this is the offset mentioned. This is the offset distance mentioned and you will draw the knife edge follower over here. That is another condition. So the second condition says that the axis of the follower does not pass through the axis of the cam, but it is at certain offset with the center of the cam, okay, axis of the cam. So this is how you should follow your knife edge follower. The follower, drawing the follower is must, it is very, very important. Also they may mention different kinds of followers, as we have 3 different types: knife edge follower, roller follower and flat faced follower. The difference that will make is here you are drawing the knife edge, in place you will draw a roller follower. Sorry, this is a roller follower, that's it. So roller follower, they will also give the diameter of this roller. Okay, they will also give the diameter of this roller, and you should draw with the exact dimensions over there. Also draw a, let's say this is, if the diameter of the roller is given to be some, let us say 10 mm. So radius will be what? 5 mm. So you also draw a prime circle parallel to this one, the least radius, in a dotted line. The diameter of this particular circle will be the summation of this least radius and the diameter of the roller follower dimension. Okay. Also, when you generate a cam profile, you have to draw the circle, the follower, in all the pitch points. You have to draw the parallel lines over here also. This is going to be the locus points of all the tracing points. We have discussed about what all those tracing points are. So this is how your cam and follower is going to be, the construction of the cam profile. Let us learn what the applications are. How and where are the cam followers used? So the application of the cam and follower basically are seen in your operating in inlet and outlet valves of the internal combustion engines, IC engines that we have seen. The reciprocating motions is observed over here. So there is a major application oriented over there. Then we also use that in a wall clocks and feed valves, feed mechanisms of automatic lathe machines. Also paper cutting machines and weaving textile machinery use these kind of cam and follower arrangements. So in this session, I think you have got very brief and let's say clear insights about the cam and follower arrangements, how they are classified, and where they are used and how they are constructed. So giving the summary of this total session, we have started with what is a cam and what is a follower, how they are used, where they are used, what is the major application. Also, we have learned about what are the terms used when we are talking about cam and camshaft and followers. Classification of the followers based on 3 different types. They are knife edge followers, roller followers, flat faced followers, inline followers, offset followers. Different types of followers we have discussed. And we have also seen the major part of this session was of the construction of the cam profile. We have seen where the stroke is given and your different motion of the follower behavior is given, and based on that how we are able to construct the cam profile. Hope this session has given you, has helped you in a definite way. Hope to see you very soon. Thank you.